Yesterday we talked about a couple different types of intermolecular forces of attraction. Right? And there were 4 of them. Hey, come on. Jacob, could you get that light for me so I can get that glare off there? Okay. We started out with dipole-dipole attractions. This is all from yesterday. Do you remember what a dipole-dipole attraction is? What does the word dipole mean? 2 what? 2 poles. So a dipole is simply just a polar molecule. And if you have 2 polar molecules, a dipole and another dipole, they're like little magnets. And they have poles. They have a positive pole and a negative pole. And then this guy also has a positive pole and a negative pole. And they're going to be attracted to each other. Generally, we draw this with a dotted line, but if I want to erase it, I have to hit back a bunch of times. So I'm just going to do it with a red line. Okay? That is called a dipole-dipole attraction. Here's a dipole. Here's a dipole. Here's a different dipole. And they are attracted to each other. That's dipole-dipole attraction. Okay? The next one, and I'm doing these fast because you should have them from yesterday, was a hydrogen bond. A hydrogen bond was a specific type of dipole-dipole attraction that occurs between a hydrogen in one molecule and an N, an O, or an F in another molecule. And I gave you 3 examples. I said H to F and H to F. Intermolecular means you've got a molecule and you've got another molecule, and if we have a attraction between the 2 molecules, that is the intermolecular force. Hydrogen is positive, fluorine is negative, hydrogen is positive, and the positive and the negative are attracted to each other. So that's the first hydrogen bond. The next one was water. Negative side and positive side. Positive side, negative side. And so if I take the positive here and attract it to the negative here, that's a hydrogen bond. Do you see how it is between the hydrogen and the oxygen? Hydrogen and oxygen. Hydrogen bonds only occur when they have a hydrogen in one molecule and either a nitrogen and oxygen or a fluorine in another. Now, good news for you is that the Regents only gives you 3 hydrogen bonds that you have to remember. HF, water, whoop, whoop, whoop. That's the one they're probably going to ask you about. They're going to say, water has blank types of bonds or blank type of intermolecular force, and the answer is going to be hydrogen bonds. Water has hydrogen bonds. And the reason that this is so important is because of those hydrogen bonds, water has extremely high boiling points. In order for water to boil, some of these water molecules need to have enough energy to escape, to leave the rest of the water molecules behind. And in order to escape, they've got to break this hydrogen bond. Imagine all of these water molecules that are in a glass. So if we have a glass of water, look how beautiful my glass of water is. I'm even going to make it blue. Isn't that cute? That's a glass of water. Okay? There are water molecules up here at the surface. When we add the heat, here, fire. Look at that fire. Sometimes there's orange. And there's yellow in there too. That is one heck of a fire, right? So when this water molecule tries to escape, when you heat it up, you're putting energy in. These water molecules over here have to break this hydrogen bond in order to go into a vapor phase. They need to now be up here as a gas. Okay? That hydrogen bond, that hug, is really, really strong. Boys, what are we doing on the computer right now? What is that? Okay, you don't need that right now. You need to be listening to me. I'm cuter than School Tool. Okay, so when we break this bond, right, the water molecules can escape off of the top. That bond is pretty strong. It's a hydrogen bond. It's not a bond. It's an intermolecular force of attraction. It's just called a bond. A bond would be inside the molecule. This is called a hydrogen bond. I know it's confusing, the words that they use, but this hydrogen bond is really an intermolecular force of attraction. It's a quote-unquote attraction between two molecules. Okay? And then that hydrogen bond's pretty strong, so that means this hug right here is pretty strong. It takes a lot of energy to get it to separate, which means I need a lot of heat, a lot of fire to get it to separate, which means it's going to be a high boiling point. I need to get it hot enough for that bond to break, that hydrogen bond to break. Okay? All right, the last type of hydrogen bond that the Regents will ask you about is ammonia. Ammonia looks like this at this point. I'm hoping that everybody can draw ammonia. We practiced drawing the last couple of days. Okay, and then you've got your hydrogen bond. Let's do red again. Between the nitrogen and the hydrogen. Right there. That's the hydrogen bond. So hydrogen of one molecule to the nitrogen of the other molecule. Here we have hydrogen to oxygen, and here we have hydrogen to fluorine. Those are your three hydrogen bonds. And hydrogen bonds are responsible for what? The extremely high boiling and melting points, because they are strong forces that are holding the molecules together. Okay? Dipole-dipole, not as strong. Hydrogen bond, strong. Then we had Vander Waals forces. You have this in your notes? Sometimes we call them London Dispersion forces. You're going to see them in the questions that I'm going to give you today to work on. London Dispersion forces. Okay, it's the same thing. Different words. Okay, Vander Waals forces happen when you have two nonpolar molecules. This is nonpolar, doesn't have a positive side or a negative side. It is symmetric. And this is nonpolar. It is symmetric. In order to get these guys to be attracted to each other, we have to manipulate the environment. We have to get it cold, so we have to lower the temperature. And we have to increase the pressure. If we get it cold, the molecules stop moving as quickly, so that they are going to be... Think of it this way, right? If I put you guys in a freezer, what's going to happen? You're going to get hypothermia. You're going to get cold. You're going to stop moving as quickly. You're going to go like this. And then you might snuggle up to one another to keep yourself warm. If I put you in a hot environment, like an oven or Florida or Arizona, what's going to happen? You're going to be like, oh my God, get away from me, right? Don't touch me. Same thing with molecules. If they're cold, they're going to huddle together to stay warm. If they're warm or hot, they're going to spread apart in order to cool themselves off. So if we want these particles, these non-polar molecules, to stick to each other, they don't want to stick to each other. There's no positive or negative poles. They're not magnets. We have to force them to stick together by decreasing the temperature, getting them to huddle to each other, and we have to press on them. We have to increase the pressure on them. Make sense? Okay. So, Vander Waals forces, two nonpolar substances. Carbon dioxide also has Vander Waals forces. It is a nonpolar molecule attracted to another carbon dioxide. This is going to be a Vander Waals force, or a London dispersion force, because they're nonpolar to nonpolar. Okay. Then the last one was a molecule ion attraction. It's exactly what it says. You have a molecule, Mostly the molecule is going to be water, with oxygen being your negative side and hydrogen being your positive side, because it's polar. Polar bears swim in water. And you're going to have something that has ions in it. Some sort of ionic compound. I'm gonna make it sodium chloride. Okay? Sodium has a +1 charge. Chlorine has a -1 charge. Sometimes it's going to be written there. Sometimes it's not going to be written there. Okay? If it is not written there, you assume you know what the charges are. How do you know what the charges are? Because we've been working on it. You get them from the periodic table. Now, this molecule comes along. It's got a positive, it's got a negative. This ionic compound comes along, and it's like, ooh, I got a positive. It's going to be attracted to the negative side of the water molecule. This chlorine is going to be attracted to the positive side of the water molecule. Okay? I've seen them ask it in the sense that they will say, here's a water molecule, orient it around a calcium. So they have a calcium here. Calcium has a +2 charge. Okay? And they'll say, put this water molecule, draw this water molecule so that it's oriented correctly around this calcium. Well, I'm going to do it with this one since I have it already drawn. Okay? The negative end of that water molecule better be pointing towards the positive calcium. And then they will tell you, all right, let's draw a couple more. Paste. Make sure that negative is pointed towards the positive calcium. You see how the negative goes to the positive? If this was negative, then the hydrogen end would be pointing. That's called a molecule. Here's your molecule. Wow. Here's your molecule. That's a molecule. Ion. Here's your ion attraction. Molecule-ion attraction. That's why ionic compounds dissociate. That's a fancy word for dissolve. Dissociate in water. They will break apart in water because that water molecule is going to pull the positive and negative ions apart in the ionic compound. Okay? And I just picked sodium chloride, but you can use any ionic compound you want. I'm going to make this bigger. Let's say this is fluorine. I don't know what I'm talking about. Get rid of that. So, ammonium fluoride. Let's say that's it. Okay? And then they give you a water molecule over here. This side's positive, this side's negative. What is going to be attracted to the hydrogen end of that water molecule? The fluorine. This fluorine right here, because that's the negative, it's going to go here. And this ammonium, which is a polyatomic ion, and you need to know that, is going to be positively charged, and it is going to be attracted to the negative end of the water molecule. Okay? So that recaps the different types of molecule ion attractions. I mean, the intermolecular forces. Let's rank them in order. Hydrogen bonding is the top. That's the strongest. Then you have dipole-dipole. Then you have Vander Waals forces. Okay, this is the order that they go in. Out of the hydrogen bondings, HF is the strongest. Then water, then ammonia. What I didn't put on there is ionic bonds and covalent bonds are even stronger than these. Okay, but out of the intermolecular forces, hydrogen bonds the strongest, dipole-dipole, then Vander Waals the weakest. Molecule ion attractions would be basically down here, but they won't ask you to rank those because it depends on what the charges are. It's called Coulomb's law. We're not going into that. Okay? All right, any questions on intermolecular forces? You ready to try to practice some on your own? Good idea. All right, let's see. Take out your Chromebooks.